Hi, this is Miss Litton, and we're going to finish up our Chapter 23, Mendelian Patterns of Inheritance, by discussing exceptions to the rules, exceptions to Mendel. This is still my Period 4 Honors Bio class. Say hi.
Hi.
All right. Now, to start off with, before, when we talked about the law of dominance, you could have a big T, and it would be dominant to a little t, okay? So the first one we're going to talk about is what's called multiple alleles. So now instead of just having big T and little t, we could have big T1, and we could have big T2, and we could have little t. Do you see how there's more than two alleles, right? That's why it's called multiple alleles. A really, really good example for that is blood type, okay? So when we talk about blood type, there are basically four main blood types, right? A, B, what else? A, B, and O, okay? Now, there's also positive, negative. That has to do with an Rh factor. I won't just set that aside. I'm willing to bring it up again, but just set it aside for now. Let's just talk about A, B, and O. This is a great example of multiple alleles. And the reason is, these are the phenotypes, but the genotypes, the alleles that you have to work off are big IA, big IB, and little I. Now, both of these big I's are dominant over the little I. So if you want to have type A blood, there's two ways to get it. Homozygous A and heterozygous A. Discuss that with your bio buddy. What do you think that would look like? Homozygous A blood and heterozygous A blood. Discuss with bio buddies. Okay, and did you say this? This would be homozygous A, right? Big IA, and then this would be a heterozygous type A, because big IA is still dominant over little I. What does it mean to have type A blood? It means on your red blood cells you have antigens for A. So you have like A's, not the real letter A. There's like 1, 2, 3, A, B, C, okay? So it's A antigens all over your blood. Okay. Now, type B blood, homozygous B, heterozygous B, same deal, okay? But this is how you would get this. Okay, discuss with your bio buddy, how do you think you get type AB blood and type O? Discuss.
Okay, it would be like two big eyes and then one diagonal.
Hang on just for a minute, okay?
And then O
What
two littles.
did you say this?
Yes, I do.
Okay, and did you say this?
Yes, I do.
Okay, now let me show you, hang on to that. Let me show you a better picture for this. Okay, take a look right here. If you are type A blood, what that means is on your red blood cells, you only have A antigens. Okay? If you are type B blood, you only have what? B antigens. Okay? Now, this is a good example of multiple alleles because you have big IA, big IB, and you have a little I. That's multiple alleles. But blood type is also good for something else. It's good to show you codominance. Codominant. So there's not one dominant over the other, because when you have type AB blood, you have both A antigens and B antigens on your blood, and both are expressed. This would be like if you had a red flower having sex with a white flower, and some of the petals are red and some of the petals are what? White. This is a black bunny having sex with a white bunny, and some of the hairs are black and some of the hairs are white. That is codominance. Both are expressed. Now, as far as who you can give blood to, you can give blood to anybody who you won't trigger their immune system. Okay? So a type A person like myself, I can give blood to another type A. Okay? And I can give blood to a type AB person, because they're not going to attack my A antigens because they have A on their blood cells as well. Does that make sense? Okay. Now, type O blood doesn't have any, it would be like this guy. It doesn't have any A antigens and it doesn't have any B antigens. That's why type O blood is the universal what? Donor. Because it doesn't have the A or the B, it won't piss off the A people's immune system. It won't piss off the B's, and it won't piss off the ABs, and you can always give it to the O. However, type O blood people can only get blood from another type O, which is great here in the United States because that's the most common blood type. Now we'll level it up. Rh factors, that comes from when they first studied it with rhesus monkeys. That is yet another one. If you have the Rh factor on there, oops, sorry, that was supposed to be an R, then you are A positive blood, okay? If you don't, this would be like B negative because it doesn't have that Rh factor. So what kind of blood could accept anybody's blood? A, B positive. Nothing would make it angry. What's the best blood to give for donating? O negative. You don't have the A, you don't have the B, and you don't have the Rh. Yeah. Now, there are other levels on the blood. Like if you're going to get, just donating somebody because, oh, she needs surgery, I need to give her some blood or something, is different than, oh, I'm going to give her my kidney. Okay? There are other things. There's M's and N's. There are other markers on there. There are really unique antigens that come together to create, where it's very, very rare blood. There are other things on there as well. Okay? So, but that is the introduction. Now, question? Okay, more? Question? Okay, so the reason why we like the blood is because it shows us multiple alleles and it shows us codominance. Okay, codominant. So on your notes, and both of these are exceptions to Mendel's law of dominance, right? Both of them are exceptions to that. So multiple allelic traits defined when a gene has many allelic forms or alternative expressions instead of just two. And then I gave you, instead of just big A and little a, you could have big IA, big IB, or little I, or any combination. Codominance is when both dominant allele possibilities are expressed, which can happen with AB blood types. Both dominant allele possibilities are expressed. So this is your first exception to Mendel's law of dominance, because before we would say big T is dominant over what? Little t. But big I is still dominant over little I, but big IA is not dominant over what? Big IB. You see the difference there? So that's an exception to that, okay, that codominance. All right, let's try this. Try this cross. Commit it to paper. Write out your genotypes and your phenotypes. Okay, write out your genotypes and your phenotypes after you do the cross. And I'm going to pause this, and you should pause it too while you work out this problem. Okay, so let's just check the setup of this problem. Okay, can I get your eyes up here just for a minute? Just make sure we're reading the setup. Cross a heterozygote type A. So what would that look like genotypically? The phenotype, I'm telling you it's A blood, but I'm telling you it's a heterozygous A, so how would that look like in a genotype?
Big I,
Exactly. Cross a heterozygous type A individual with a heterozygous type what? B. So that has to be big I, B, little I. Did you get that far? Okay, so your Punnett square would look something like this for your setup. Did you do that? Okay, so let's take a look at how this would play out. The genotype would be big IA, big IB. That's the genotype right there. What would be the phenotype of this blood? AB. Okay? So genotype is big IA, big IB. Phenotype is AB. So do that for the rest of them. This should answer your question. Just pause you for a second. Okay, come back up to me, okay? So this next one, the genotype is IB little I, but what's the phenotype here? What would you just say? B. And this one is IA little I, but you would say phenotype A. This one's genotype is little I, but the phenotype you would say it's O. Okay? Ask your bio buddy, you got questions or concerns on that? Do you get it? All right. Now, I'm going to tell you that there are practice problems, okay, that you could do. You know, like there's a full-on who's your daddy in here and things like that. So that would be practice problem set 4. It's in your book. Where are the answers to those practice problems? Yeah, I'm not giving it to you as homework. I'm just saying you should do this because this would help you, right? That's why you're doing it, all right? Now, let's go back and revisit what we talked about earlier today, okay? Females in this room, biological females. You got an X chromosome from your mom and you got a X chromosome from your dad. You are 2 X's. They will play themselves out, dominant and recessive, just like all your autosomal diseases. So there's no exceptions to your rule if you are a girl. However, if you are a boy, how many X's do you get? 1 X, okay? 1 X is all that you get. And so what you get, and you're going to have to, you will express it. It doesn't matter if it's recessive or dominant. So that's why it's an exception to Mendel's law of dominance. Okay, and then what I want you to do is go into Hello Smart and then walk out that door of Hello Smart. I'm going to pause you for a minute. I did like bird dogs. Okay, come back to me. Now, I don't know why it's not saying no one answered. I don't know why it's having trouble with this, but what is the right answer to this one? 8. And I don't know if you got that or not. Now, there are various forms of color blindness. Not all are on the X chromosome, but I would be most interested in the males in the room if any of you missed it, because you're most likely to have it. What number is number 2? 5. Okay, see if your bio buddy got it. Number 3 was what? 15. Check to see if your bio buddy got it. And what was the last one? 73. Yeah. All right. Now, let me talk to you about color blindness. Okay. Now, what is annoying to me about color blindness is that they use the letter B. Because color blindness is not a dominant trait, it is a recessive trait. Okay? But you'll notice it's a superscript on the X, not the Y. So X big B, XB is actually a normal female. You got that? All right. So I want to play this out a little bit. Can I grab you? You're going to stand right here. Can you come on up? You're getting married? Yes? Come on up. How cute. Look, they're married. All right. Now, oh yeah, you can't see this, so I'm pausing you. Sorry. Remind me to restart it. Okay, I'm going to try, so hang in there. Okay, so what we have right now is we have a normal female. That's like X big B, X big B. Do you see that? And we have a normal male. What are their odds of their boy, make a little boy. So you got to give your Y. There we go. What are their odds of the boy having a disease? They're both normal. So what is the odds of a boy having a sex-linked disease? 0. What about a girl having the disease? 0. Okay. Now, let's be the second genotype, X big B, X little b. So I'm going to trade out one of Mama's X's for this bad X. Okay? So she right now, does she have the disease? No. There are sex-linked dominant diseases. I'm not going to give you any because those are hard to differentiate between autosomal dominant. The only ones I will give you are sex-linked recessive. So she right now is a carrier, just like a brown-eyed person could be a carrier for what? Blue eyes. Okay? So does she have the disease? No. She is just a what? Carrier. Does the dad have the disease? No. Okay? If they make a little boy, what are the odds that the little boy will have the disease? 50%. 50%. To make a little boy, he's got to give the Y. Half the time she could give a good X, half the time she could give a bad X. Okay? Now go back. What are the odds if they have a little girl if she has the disease? 50%. What do you think?
50.
The little girl will not have the disease. Why? The dad will always give the good X. Half the time, hold that up there, half the time, no problem. The other half the time, the very worst they could have is they could have a what? Carrier. Does that make sense? Okay. Now, let's switch. So now the dad is the carrier, the mom is perfectly fine. Okay. What are the odds of their son being colorblind? 0. We don't care what the dad has, because if they have a son, he's going to give the Y. And both of her X's are good. What are the odds that their daughter will have the disease? At the very worst, she will be a carrier. In fact, that's the only thing she will be, right? Mom will always give a good X, but dad will always give a bad X. So all their daughters will be what? Carriers. Does that make sense? Okay, now let's do this. Okay, give him a good X. Okay, and let's do this. Okay, is Mama colorblind?
Yes.
Yes, Mom is colorblind. What are the odds that their sons will be colorblind? 100%. Because to make a son, he will give the Y, and every single X she has to give is about X. Do you see that? What about their daughters being colorblind? 0. But they will be what? Carriers. Do you see how that works? So you have to play it out whether it's boy or girl and who has the disease. If mom has a sex-linked disease, what can you say about her children? All of her sons will get the disease, and all of their daughters will be carriers. But if the dad also has the disease, right, everybody gets it, right? There's no escape from that one. Does that make sense? Okay, good job. Sorry, you're now divorced. Okay. So, let's take a look here. Okay, do this cross right here. I'll give you time. Do this cross right now. I'm going to pause. Okay, just to make sure you're on the right path, if you haven't started this, please pause this video and try to do it, okay, before I start showing. Okay, if I'm going to have a normal vision man, how would I write normal vision man? Can you be up here? Help me. How would I write normal vision man? X what? What? He's a normal vision. Remember, it's weird. Remember, normal is big B. I know, it's annoying. I know, it's annoying. He is XBY, and he is a normal male. Okay, who are we crossing him with? Yeah, so how do we write that? X, big B, X, little b. Are either one of them colorblind? No. What can you say about the mom, though? She's a carrier. Okay, keep going. I'm just going to set up the Punnett square. By the way, what number is that? 45, yeah. Incomplete dominance? Oh yeah, I did, because this thing doesn't scroll. I need to go back to incomplete dominance. Sorry about that. I was like, I don't remember what I was talking about. Okay, be back here with me. X big B, X big B. What is this going to be? Before I reveal it, what is it going to be? Oh wait, did I unpause it? Oh, I did. What is it going to be? What is it going to be? Male, female, colorblind, not colorblind, carrier, what? Female, normal. Yeah. What's this one going to be?
Male, female.
Male? Female what? Carrier. Good. What's this one going to be? What's this one going to be? Male carrier? No, male what? Colorblind. Okay, so this is an exception to Mendel's law for boys, right? Because they only have one shot at their X. And I gave you all the notes for colorblindness. Do you see that? Okay, and for some reason I skipped over the other, so now I'm going to work my way backwards. Do you remember when we talked about codominance with the AB blood. The next, yes? So both alleles were expressed. The next one I want to talk to you about, so I go back to this in your notes, is incomplete dominance. Incomplete dominance is like a red flower crossed with a white flower and all the offspring are pink. A black bunny crossed with a white bunny and all the offspring are gray. Okay? That is incomplete dominance. Codominance, both traits are expressed. Black bunny, white bunny, the babies have black hair and white hair. Incomplete dominance, black bunny with a white bunny and all the hairs are gray. You see the difference between the two? Okay, so here's somebody who has straight hair. Notice their genotype is H1, H1. H for hair, 1 and 1. I like that because they're both straight. The number 1 is straight. Okay? To have curly hair, you are what? H2, H2. 2s look curly to me. If you cross a homozygous straight with a homozygous curly, you will get a heterozygote incomplete dominance wavy hair. Okay? What I want you to do is I want you to do a Punnett square, cross 2 wavy-haired, they need to grow up a little bit, but cross 2 wavy-haired individuals. Try it at home too. Okay? So look up here. What's this individual? What kind of hair are they going to have? Straight. What about this one? Wavy. Okay. And when you're dealing with when you're dealing with incomplete dominance, the genotype matches the phenotype. And that's because every single genotype has its own phenotype. H1, H1, because nothing's dominant over the other. H1, H1 is straight. The other genotype you can have is H1, H2, but that will always be what? Wavy. And H2, H2 is curly. Every genotype has its own phenotype. That's how you can tell when you're dealing with an incomplete dominance. Again, an exception to Mendel's law of dominance, right? So we've had codominance as a result of multiple alleles. We've had incomplete dominance, also an exception to Mendel's law. And then we had sex-linked traits, where it's the men. It doesn't matter about dominant or recessive traits because they only have one shot at it. Okay, ask your buddy, how you feeling on that? All right, and then, sorry, I cannot scroll. All right, next, let's see, I don't think I asked you this question. Let's see how you do on this. Showing the question so you can see it if you're at home. We're going back to sex-linked traits. Okay, make that commitment. All right, so let's talk about it. If a boy is colorblind, what's the genotype if a boy is colorblind? Be this, right? I am that boy, okay? So if a boy is colorblind, 3 of you said his father must be colorblind. Does his father have to be colorblind? No. Why? What did his father give him? The Y. So I don't care what his father was, colorblind, not color. He definitely doesn't have to be colorblind. All he has to do is be able to give his boy a what? Y. 6 of you said B and D are correct. So let's look at D. His siblings are also colorblind. Do his siblings have to be colorblind? No. His siblings don't have to be colorblind because it could be that the dad is perfectly normal, good X, good Y, and the mom's a carrier. So maybe the other children are not in any way colorblind, you see? So we can't determine that either. Check with your bio buddy, see if they got that right, or did they struggle a little bit. Okay. When you look at pedigrees, okay, so this is a good example of a pedigree for somebody who's colorblind. Again, the first thing I look at when I look at a pedigree is, are there a lot of it or a little of it that have the disease? In this case, is there a lot of it or a little of it? Little of it. So if it's a little of it, the next thing I need to ask is it autosomal recessive or is it sex-linked recessive? What I would look for to decide that is, are boys hit with it more than what? Girls. If boys are hit with it more than girls, then it is probably a what? Sex-linked trait. One thing to look for in sex-linked traits is a daughter will only have the disease if, finish that sentence. A girl will only get a sex-linked disease if. Does the mom have to have it? Does the mom have to have the disease? No. She could just be a what? Carrier. Does her dad have to have it?
Yes.
Yeah. A daughter will not get a sex-linked disease unless her dad has it. Because he has to be, his X has to be bad. For sex-linked recessive disease, you got to get 2 bad X's. Your dad's got to give you one of the bad X's. If he has a bad X, he has the disease. Those are the patterns that you look for in that. Here's another one that you can see where you're tracing it back. Okay, so if you notice right here, she has it, but she's not part of this family. You see that? She married into this family. Got that? Okay, here's an example of it, Duchenne's muscular dystrophy. Hemophilia is a sex-linked disease, and this happens in European royals because they're making treaties and things by marrying children, and they kept inbreeding, and their genes that were recessive kept showing up, specifically hemophilia, and then they're dying of that. Okay. Next exception to the rule is polygenic traits. What does poly mean? Multiple genes. This is not multiple alleles. Multiple alleles would be big T1, big T2, big T3, and little t. This is polygenic, which means you have T's, R's, Q's, and P's giving you your trait. If you look around this room, there are variations of colors within this room. Okay? It is not black, white. Okay? We have brown, tan, very black, kind of black. Okay? We have all different colors because it is a polygenic trait, just like your eyes. It's not like they're black, brown, blue, that's it. There's a whole spectrum on there. And so that is a polygenic trait. Remember what I told you about intelligence. It's not big S, super smart, big S, semi-smart, little s, super stupid. Your intelligence is a polygenic trait. In fact, most of the traits you have are polygenic. There's more than one gene. We're not like pea plants where we are round or wrinkled. We are tall or short. It is not that. It is polygenic. So you tend to see a bell-shaped curve in polygenic traits because so many different genes are contributing to it. Here's one for you with height. They did happen to put the males in blue sweatshirts and the females in white, but you can see that curve, okay? And polygenic traits tend to be impacted more by environmental factors. So, for instance, this is a Himalayan rabbit. His ears, face right here, and feet are black. But if you shave his back and put an ice pack on it and leave it there, I don't know how long you have to leave it on there, maybe a couple days, and then you take it off, the hair will grow back black. Now, why would that be adaptive? What do you know about the black color? What does it do? Absorbs every wavelength of light. His little feet are running on cold snow. If his little feet are running on cold snow, it would be better if they were warmer by absorbing more light. His face, breathing in cold air, keep it warmer. If it was black, and then his ears sticking up, they're all thin, right? They could easily get cold, so it'd be better. So your environment can influence your phenotype, how it is expressed. Reptiles are more, you can determine the sex of the reptile by the temperature of the nest. We'll determine that. And so that brings in your whole nature versus nurture argument. Is it in your nature? Is it in your DNA? Remember when we looked at that already? Or is it due to nurturing? It brings all of that in. And these polygenic traits I'm telling you about, especially these disorders like cleft lip, schizophrenia, certain allergies, they are more susceptible to environmental influence than other traits that are not polygenic. Okay, so on your notes, if you could go to polygenic inheritance. These are defined as when one trait is governed by two or more sets of alleles. When one trait is governed by two or more sets of alleles. And your example is skin color. Environmental or multifactorial traits. I don't know why those women are there. I'm sure they're not packing heat, but they're not supposed to be right there. Multifactorial traits are traits. Do you have trains? Yeah. Change it to traits controlled by polygenes or subject to environmental influences. And then I gave you some examples. Hi, can you help me right here? Oh, okay. We just can't have people on the campus right here unless you have a pass. So if you wouldn't mind, just because otherwise it would be 2 hours. I see.
I wasn't planning on her coming with me today's my day off.
Oh, okay.
She's still following me out the door.
Okay. Okay, I wanted to hear about that. Okay, hashtag kindness. Okay, so then there are some examples of different diseases that are right there. Okay, next and last, did you think they were coming in? I just had to go talk to those ladies and tell them to shoo, and she was giving me her life story. Okay, the last one, more practice problems for that, and then linked genes. This is something we talked about at the very beginning, where you could have 2 traits on the same chromosome. So in this case, wherever big A is going, who's going with it? Look up here. Big A, big B. Okay? Wherever little a goes, who's going with it? What did we learn in our cell division chapter that could potentially break up this gene linkage? Crossing over. Okay? And this is the last part of your notes. So crossing over could break up that gene linkage. If you go to linked genes defined, all the genes on one chromosome form a linkage group. All the genes on one chromosome form a linkage group. Genes that are linked together tend to travel together to the same gamete. Genes that are linked together tend to travel together to the same gamete. Okay, and before I give you the last bit, I want you to take a look here. What genes do you think are going to experience more crossing over? What genes are going to experience more crossing over? Z and G or R and G? And why? Tell that to your bio buddy. Tell that to your bio buddy. Z and G or R and G? Where would you expect to have more crossing over events between to break up the linkage? Z with R or Z with G? What do you think? Give me your gut reaction. Z with, well, let me show you. If you want to break up the linkage between Z and R, is that what I asked you? Z and G? R and G, right? R and G can only cross over right here to break up the linkage, right? But if you want to break up the linkage between Z and G, you can cross over at all those places plus all of these places. You see that? And so you are more likely to break up the Z-G linkage than the R-G linkage because you have more opportunities to break it up. And that is how they can map out genes. If a lot of crossing over events occur, you're probably far away on the chromosome. If not so many, you're probably close. So an example in your life is hair color and eye color. Those are linked. So people with dark hair tend to have dark eyes. And people with light hair tend to have light eyes. So if you're somebody who has dark hair with blue eyes, you are a result of a what? Crossing over event. Okay? Now, for your last 5 or 6 minutes, okay, I would like to give you the opportunity to model mitosis and meiosis real quick with your bio buddies, okay? You can do, oh, I got to give you some notes. Right, thank you. That helped. Form a team, then just come up and grab teams of 4, okay, not teams of 2. Grab some chromosomes, model. I gave you, if you look in Google Classroom, I gave you specific instructions. Nothing you have to turn in, but I would know how to do what I gave you on those instructions because it's something I will ask you on a test. I'm just giving you something to model that with. If you're done and you want to eat your model, you can, okay? But when you form a team, it's right here. Let me give you that last bit of notes. Okay, the last bit, hush. Number 3, crossing over is the only way that linkages are broken. The only way that linkages are broken. Okay, what else?
I think we missed the incomplete dominance.
Oh, the notes for it? Okay, we did because I skipped right over accidentally. Incomplete dominance when a heterozygote has an intermediate phenotype between that of either homozygote. Intermediate phenotype between that of either homozygote. And your example is red flower across the white flower could make what? Pink flowers. Pink. Okay? Go model with your bio buddies. Make good choices.